So in this part, we are going to look at the topic of evaluating machine learning algorithms. So let's start looking at what evaluation is. Basically, when we say evaluation, what we try to do here is how predictive our model is. So we learn how to build trees, rules, use of nearest neighbors, probability, calculations for naive Bayes and so on. So, but then we need to predict for new data. But remember one thing: if you are using a data to train, if you are using the same data to evaluate how good your model, it's not a good indicator, because we will see usually you will get very high accuracy when you build a model and if you use the same data to evaluate your model, right? Because your patterns in your training data will not be same as the patterns in the new data. So this is something that we have to be taken care of. Right. So with that said, we need to focus on something called overfitting idea. Overfitting means that usually you get a very high accuracy during the training. That means you build the model and then you see, okay, you will have very high accuracy in the training part. But when you test, you might get a very low accuracy. If that is the case, we call this as overfitting. So overfitting means you build a model, looks really good, you got good accuracy with the training data. But when you test with new data, you might get very low accuracy. So you get a good accuracy with the training, but the testing or evaluation, you are getting low accuracy. This is called overfitting. Similarly, there's another concept called underfitting, which I have not described here, which means you are not getting good accuracy for both training and testing. So that means you have not enough data to learn the concept properly. So this is called underfit, right? But overfitting is what we want to avoid, especially when you are going to evaluate. So when you are evaluating your models, there are different measures we have to use. We normally use error rate or accuracy. We use these two terms interchangeably. Error rate, the opposite is accuracy, right? So therefore, we normally look at classification error or classification accuracy. Right, starting from the error rate, what it means by error rate is how good our model is for classification problem. So whenever our model can predict a new data correctly, we call it a success. If not, it's a error. So we say it's a success, and then if not, it's an error. So what I mean by error rate in this case, proportion of the errors over the whole data set, right? So given a particular instance set, if you can, find out how much error it makes compared to the total number of instances, then we can find out the error rate. Opposite way, we can find the accuracy. So accuracy means how much you can successfully predicted divided by the total will give you accuracy. So I'll come to that later today. In the slides, we have these measurements. Right. Now, one of the things you have to be very careful is when you say accuracy or error rate, you should not, focus on your training set accuracy. So we'll see that when we build the model, usually we don't use all the data we have. We separate the data as training and testing. Why we are doing this? Basically, we need to know how good our model is. To do that, we do the evaluation part, and that's what we are going to discuss it here. But remember, the accuracy of the training set or error rate of the training set, it's not a good measurements. We normally call it optimistic. You will get very high accuracy. So the reason for this is any random data, you might be able to find some pattern, right? That's the reason for this. Right. Now let's look at how we should build model for evaluating them. Now, to do that, we have bigger data, we have large data set, we have medium, we have a small, and so on. So what I mean by large here is you have enough number of data. For example, if you take images, nowadays you might be able to find quite a lot of images, right? Available, because with the web and people are sharing images, you might be able to find a lot of sources for them. But then there are like some applications like cancer data. If you take about like, okay, predicting a cancer, number of data reports will be very small. We call very small data. So let's look at how to evaluate if you have enough data points, right? So if you have enough data, that means if you have thousands of data points, right, and which includes enough number of instances for each class, because we are going to look at only classification problem. So you have different categories, like in our case, play yes and play no. You have to have enough number from the both classes. So if that is the case, how do you evaluate? So usually what we do is we separate the data as training and testing. There are people actually come up with various different ways. Some people would say like 80 to 20, 70 to 30. And in my case, okay, we go with the 2/3 and 1/3. This is the default, how do you separate in WEKA software. So that's why I have taken these ratios. So we split the data randomly. What I mean by randomly here is there could be many ways to separate the data set, right? So we'll take 2/3 for train and 1/3 for testing. And what we do, we build the model using training and test using the remaining. So you build the classifier using the training, and then you want to know how good our model is, because test set we also have labels. So we allow our model to make prediction when we compare how good our model prediction is based on the test data. So that's what we say evaluation, right? Okay, so let's look at graphically how do you do that. Get a data set, and usually you will have positive and negative. This is the class labels. So you separate the data as training and testing. Okay, in our case, we'll take 2/3 of the data set as a training and 1/3 for testing. Next, use the training to build the model. What do we mean by that? Okay, use a decision tree classifier, then you get a tree structure. Use a decision rule classifier, you will get a rule set. Use naive Bayes, you will get the probabilities. So this is the model, right? Then once you use the model, then use the test set. So use your testing set, using the model you build here, you evaluate, you see how good they are. So for example, without considering labels, you can make predictions and you can compare it with actual labels. So this is called the prediction. So this will give you evaluation of how good our model is. For example, if you test, you might get like, okay, 80% accuracy, 90% accuracy, 60% accuracy, and so on, right? You will get how good your model is based on the testing data set. Okay. Now, that's how we do. But then there are some issues most of the time, right? When you look at like different types of data sets, the data is not equally distributed. What I mean by this is there are many cases we'll see the data is not the same, right? That's why we said you will have very unequal frequencies. That means you have enough number of data for one class, but not for the other class. Let me give you some examples. So for example, if you look at prediction, what I mean by this is people actually switch products. You are using like some mobile connection, and then when you get a new offer, you switch the mobile service provider. Similarly, you use some particular product or service. When you get a better offer, you go with the other one. Usually the fraction is about 97% of the time people would stay with the same service or some product. About 3% will switch. Now, what we want to do is we want to identify these 3% correctly, and we want to retain them as customers. So those who works in the business domain, they know that how difficult sometimes to acquire new customers. So they are focusing on retaining their existing customers. So they want to identify who's about to leave their product and services, and then they are going to keep them. And that's exactly the problem. Similar goes with the medical diagnosis as well. Many of the diseases, the number of patients, the information is scarce, which means we don't have enough information, right? Again, the classes are not balanced. Think about the e-commerce, the website. Majority of the customers who visit the page, they don't buy anything from the web. So 99% of the time, they don't buy anything from your website. 1% is likely that they purchase something. But remember, when it comes to predicting, this is the minority class is the most interesting part. We want to correctly identify those who are going to buy something, but not those who just come and leave. Similarly, security, right? Let's say terrorist access, terrorist activities. You might say that, okay, more than 99%, 99, they are not terrorists. Okay, which might very biased towards the positive, but what we need is the other one. Those who are terrorist information, right? We want to get it. So likewise, many of the applications now you will see data is not balanced. And this is a one problem you have to identify. If you have a data, but data is not balanced properly, then we have to do something about it. So same goes with if you have multiple classes. If you have two class problems, okay, we want to have data as 50-50. If you have three class problem, we want to approximately take 33% at a time. Okay, so with that said, right, you can, use the classifier. Remember that if you are not treat very well these, classifiers, when you work with unbalanced data, that means if you are not doing a justification for the data distribution, what might happen? Majority classifier classifies correctly because you will see it biased towards the majority class. Okay, let's start with the first one. So in the first application, majority is those who are going to stay with them, and 3% is those who are going to leave. So what we are interested in the 3%, not the 97%. And usually when you build a model with such distribution, you will get better accuracy for those who are stay with the company, not those who are not going to switch, right? So this is the problem. Similarly, e-commerce, if you build the model as it is, we have 99% don't buy and 1% buy. So you will have a better accuracy for don't buy, not for the buy. So this is the issue. Majority class can be correct most of the cases, but it's useless because majority is not what we are interested. Right, now let's look at how to balance the data. So ideally, let's say you have two classes and there are many ways that you can build, train and test. So ideally what you do is you will select a desired number from the minority class first. Let's say you have 60 data points, okay, take 50. And then what you do is you are going to add equal number from the majority class. So in our case, let's say you have 60 data points and you are selecting 50, and we should get 50 from the other class so that we can create a balanced data set, right? So that's what we need to do. The question is, how do you generalize balancing, especially if you have multiple classes? So if you have multiple classes, this is about the two classes, but if you have multiple classes, it will be the same, right? If you have multiple classes, what we need to do is we want to make sure that each class represent approximately the same when you are dividing as training and testing. This is for any number of classes. Right. Another idea that we need to be very careful of is parameters. What I mean by parameters, I hope you remember that our very first classifier, 1R, when we discretize, we talk about something called number of bins, which means how do you consider the maximum number of instances from each class when you discretize, when you look for ranges. So these are called parameters. Parameters are learned during the training. So, but you cannot directly use your training data, and it's not good. But remember, you should not use your test data set as well. So during parameters, when you search for parameters, you should not use your test data set at all, right? So it should not be used for the training. So keep this in mind. So some machine learning algorithm, you can find two stages. So first stage is you build the basic structure. Second, you optimize the parameters. It's like you build a tree and then later on you change other parameters, right? You can change number of records, you can change how you actually calculate the importance and so on, right? But remember, test data set you should not use to identify any of these parameters. So therefore, if you have a situation where you need to identify some parameters of the algorithm you have chosen, then we have to divide the dataset as three parts. The common ones are we can have like 80% for training, 10% for testing, 10% for evaluation, right? If you're using 70% for the training, then you can take 15% at a time. So likewise, depending on the number of documents, you are going to select this. And when you separate the data as three different units like training, validating, and testing, remember, validation data is used for optimized parameters. So it might use to find out the best k-value and so on. Right. Next. Now, remember we separate the training and testing for evaluation purpose. Therefore, when you build your final classifier, you should use all the data you have. Okay, let me show you this because I think we discussed enough. So let me use WEKA to elaborate this one. So I'm going to, okay, so let me start with the Explorer. And let me open up a file. So I will go to C, then program files, WEKA, and data to discuss the implementation, real implementation. So I'm going to use iris dataset. I hope you remember the iris dataset. This is about classifying three different types of flowers: iris setosa, versicolor, and virginica. And there are 4 measurements, right? Okay, so let's go to classify tab. Remember, these are the things that now we are discussing. We are discussing the evaluation part. So let's select the percentage split here. This is what I have discussed, like separating data as train and test. So in this particular case, we'll take 66% for training and then 33 for testing. There are other information is also here, right? Next one, you can choose the model. So I'm going to select tree and then J14. So what happens? We separate the data as training and testing. 66% we use for training and 34% for testing. So let's start and you will get the tree structure now here. So let me show you by visualizing it. So when you visualize this, you will observe that, okay, here is how the decision tree is built. So we start with the petal width. If it is less than or equal to 0.6, it is completely, separated as iris setosa, right? And then you will see the other parts of this, right? So basically, this is for the evaluation part. And ideally, you can notice that the evaluation part comes here. In evaluation part, you normally see how data is actually gone into different, leaves, right? That's what we have observed. And the outcome is actually coming from full training. Remember that it uses a full training set. Although we separate 66 for train and the remainder for test, the model actually uses all the data. So separation will happen, right? We separate the data as training and testing because it's only for evaluation. So here is the evaluation. So it says currently with our train and test plate, it says, okay, it's correctly classified 96%. And you can see we have about like 51 data points. Basically, it's separated into, 33% and then, 34% and 66%. That's how they have separated the data. And that's what we have observed here, right? So this is the measurement we can look, and this will be based on the test data that we have observed, right? Okay. So I hope you got the idea of how do you separate and training and testing. As I told you earlier, usually if you have enough data points, we recommend to go for train and test split. But if you do not have enough data points, then it is not a good technique to separate train and test, right? So let's look at how we are going to handle this model sets thing. Right, going back. So we have observed that when we build the model in WEKA, what it provides is the final model built on top of all the data points. Understanding this is very, very important. Right. With that said, let's move on. So generally, when you have more data points, you have a better classifier. Right? So that's why we have observed in the real life as well. Earlier, we have GPT-2, GPT-3, GPT-4, and so on. And this is mainly because the development with you have larger data set. The number of data points you use for ChatGPT-2 and ChatGPT-3, in 3 you use more data than 2, right? So that's what, this is a general observation. Many of the time, if you provide more data to your model, you will get a good outcome. More the data, more the accurate your models are. Right, next. Okay, this is what exactly it means. The larger the test data, the more accurate their estimate. Okay, so this is what I discussed earlier. More the training data, you get the better the classifier. But if you have more test data, then you have more accurate error estimate. What do you mean by error estimate? Mean how accurate your model for new data. So this is the trade-off. And that is what we use to decide whether do you use 80 to 20 or 70 to 30. Okay, so let's look at the overall picture now. So ideally, if you have parameters to optimize, what you do is you take the data set, you split is train and test, and then you build a model, and then you get the model, and then you have the evaluation for this, right? So once you do this, you use everything to build the final model, and then you will have an independent test set to evaluate how good our model is. So usually this is the process that we observe. Right. Now, separating training and testing is okay as far as if you have enough number of data points. But if you do not have enough data points, so separating training and test would not be enough. Therefore, people started looking at cross-validation. So let's look at what cross-validation does. So cross-validation meaning like you are going to get different test sets. So you separate the data into subsets, take a set, you keep one aside as a test set, take the remaining for the training data, and then you are going to evaluate this, right? So you use divide into K subfolds and take one out, take the remaining for the training and use the one is for testing, right? And this is called K-fold cross-validation because you use K here. If you look at the literature, you will see that most commonly we use tenfold cross-validation. What I mean by tenfold? So tenfold means you separate the data into K and then take the one out, work with the remaining, and we build the model, right? So the other point is when you are going to make subset, you have to make sure that if the data is not balanced, you have to keep the same ratios. That's what we call stratified because the same ratios are preserved here as well. Right. And then since you are doing this for K times, because you divide into K folds, you build the model using K minus 1 and test with the whatever remaining. And this will be repeated multiple times, and then you will get the average value. Right. Let's look at how graphically we can represent. So what we do is you will get a data set, separate into groups and take one out, use remaining to build the model. And then you repeat this process for all the folds and then consider the average value. Right. Now, when you talk about the tenfold cross-validation, we will also use another name together. This is called stratify. So stratification meaning that you have same proportions in the data in training as well. So we divide the data set as training and testing, and both data set you have the same distribution. That's what stratified means. Remember, I told you you will have 99% don't buy and 1% buy. Of course, when you're separating out, you will have the same relation, right? If you want to capture this. So this is called stratified tenfold cross-validation. Stratification means you are going to keep or you are going to have the same proportions as in trade, right? Now, if you're wondering, I told you this cross-validation is actually based on the n number of folds. So we decided to use 10 folds and the question for why 10? So this is based on the experiments done by people and they have reported in the scientific domain. And they have showed that the best choice would be considers of 10 folds. And that's how the 10 came into the picture, right? So we are using 10-fold cross-validation. And same way, if you are using stratification, same proportion you will see, right, in the subfolds as well. So this will reduce the variance of the estimation. Right. And what is much better is you can repeat this again. So cross-validation, we repeat, let's say 10 times, and then you can have repeated stratified cross-validation, which means you are going to repeat for another 10 times. So which means 10 into 10, it will be 100. So that's why it means here 10 into 10 times 10-fold cross-validation. Right. Now that we have understood about how to build your model, which means knowing how good your model for new data, Let's look at how to compare various different algorithms. So in this part, we are going to discuss how to compare this. Well, when it comes to comparing this, usually can use some statistical test as well, right? So when you're comparing, one of the problems that you are going to face is which model you are going to use. Let's say you are going to use decision trees and then let's say naive Bayes. If the recorded accuracies are almost the same, okay, so how do you handle this? That is the question, right? When you compare. So this is actually domain dependent problem, right? So basically you can go for tenfold cross validation if you have the same thing. But again, the problem is variance. What do you mean by variance? Okay, when you have multiple different accuracies, you can find the average accuracy and you can find the variance, which means how far you have deviated with the average, right? And this can be reduced using repeated cross-validation. That's what we discussed. So only problem is we are not really sure after even we do this, we are not still sure whether the results are reliable. So for that, we need to use some statistical tests. So usually we are going to ask a question like how good or how significant our accuracy is, right? For that, we can use significant tests. So significant test means how confident we are, right? And how the data is different and how you get different accuracies. So we have already seen last time at the end I showed you, you can select one, right? And compare with all the other algorithms. Right, in here, in the test, what it does basically, it has both null hypothesis and alternative hypothesis. So you start saying that, okay, there's no real difference. So for example, if you take accuracy 60 and 62, usually you cannot find any significant accuracy difference between them, right? So null hypothesis, we set it as, okay, there's no real difference. But then alternative hypothesis, we said that's, okay, there's a difference when you're comparing, multiple algorithms. So in significant test, in summary, what we try to do is we are trying to measure how much the data actually in favor of rejecting the null hypothesis. Right. So if you're using 10 times 10-fold cross validation, and then we can get the average accuracies, and then you can identify whether they are significantly different. So you can use students pairs t-test, and it tells us whether these means, the averages, right, are significantly different. So that's why I said, when you say 60% accuracy, 62%, okay, you don't see big difference, but what is big and how do you identify? And that's for that, statistical test will be helpful. Right. Now that we have understood this idea, let's discuss how are we going to predict the various different measures, right? And to understand this, we are going to look at a matrix. So in that matrix, you will have true positives. What do you mean by true positive here is your actual class is yes, then our model is also predicted yes. So if the both cases are yes and yes, we say true positive. What do you mean by true positive? The actual labels are correctly predicted by the model. And when you say no, what it means at this point is your actual class is yes, but your model predicts as negative. And therefore, this is called false negative. Why we say false negative? Actually, the actual class is yes, but the predicted as no. Similarly, the other error is the actual class is no, and then our model is predicted as yes. So this is called false positive. Of course, actual class is no, and predicted is also no, then we say it's true negative. Right. So these are the measurements normally we can use. And using this, we can define other measurements. So sometimes this matrix form we call confusion matrix, right? So which will indicate the true positives and true negatives. So if you look at the machine learning techniques, usually they are trying to minimize the false positives and false negative. That means these parts, we are trying to reduce these two values. Right? Marketing domains, basically, they are trying to maximize the true positive. So that's why depending on the domain, what you are going to optimize might be different. Right. Sorry about this. I'll go back. Right. So I think you got the point. Let's move. So there are a few measurements that you should be familiar with. The first one is we call the accuracy. What I mean by accuracy in this particular case, we find out the true positive. That means actual is yes. Model is predicted is also yes. Actual is no. And the model is also predicted no. Right? So these are correct classification. Divide by all. So this is called accuracy. Similarly, there are other measures as well. Right? What are the other measures? There's a measure called precision. I'll come to this in a separate slide. Basically, what happens in the precision part, you get the true positive. What do you mean by true positive? The actual class is predicted correctly, right? The positive is predicted as positive. That is the case, we say true positive. Divide by true positive plus false positive. What do you mean by true positive plus false positive? All the attributes are considered as relevant, right? Similarly, recall means same thing, true positives. What do you mean by true positive? The actual values, right? The labels correctly identified by the classifier. Divide by true positive plus false negative. What I mean by that, all the relevant documents, everything, all the positive elements are considered here. We call recall. And the final one is called confusion matrix, which actually gives you a distribution of how accurately we have identified. So in this particular simple graphic, you will see there are three classes, actual classes, and this is predicted classes. So if you take this number 88, what means the 88 instances, the actual class is A, is also predicted as A. So if you go diagonal, that is correct classifications, right? So actual class is B, predicted as B. Actual class is C, predicted as C. Right? Similarly, you can see the off-diagonal element. These are diagonal elements. Off-diagonal elements are the, errors the classifier made. So those are the errors made by the classifier. Right. Now that we have understood about the accuracy, precision, recall, confusion matrix, let's move to the next. I want to first focus on the precision and recall because these two measures actually got popular in information retrieval. So let me take an example, and this is from the Wikipedia, where they describe what is precision and recall. Now, let me take this example. It's like this. Let's say we have documents. Okay, let me put it like this. When you search some document in the web, let's say you are going to use Google. There are relevant documents, but the query will return something. So this one indicates all the positive and negative. Let's say we have a query. What is relevant for query is we call what is relevant, true. And then we have positives and we have negatives, right? So now we have, these are like what is the relevant documents. Out of these relevant documents, when you perform a query, you will get something which is relevant here, as well as some are not relevant. It's coming from the other class. This is called selected documents. So we have selected documents. When you type a query in Google, you get some documents. Some are relevant, some are not. It's like this. Some are relevant, it comes here. Some are not relevant, it's here. Right? So those are the relevant ones. And when we are selected them, we call true positive. Otherwise, we say false positive. Right. Now let's look at the graphical version of the precision recall. So the precision means, okay, the retrieved document out of which you will have the actual relevant documents divide by total number of documents you have selected. Right? This is predicted, right? So this part predicted positive. This is actual positive. What do you mean by actual positive? So the labels are positive and then predicted is positive. So this is the precision. So which indicate how many selected items are relevant. Yes, how many? This is the selected elements. This is the selected elements. Out of that, how much are relevant? That's what precision means. Similarly, if you look at the recall means you will take the relevant documents, divide by all the relevant documents. So this part from here. So what the query is similar to how many relevant documents, relevant items are selected. So that's what the precision and recall are. Of course, there are many others, but most commonly used one is called, we have precision and recall. And instead of, reporting these two values, there's another measurement called F measure can be used, which combines both recall and precisions. So in this one, you will notice that the use of F measure, right? So you can, like accuracy, can use F measure, which considers both recall and precision. Right. The next part, yes, which measure are we going to use? Right. What I mean by this, we have precision, we have recall, we have F measure. Which one? Okay. Ideally, you better look at all of them. If all of them are better, which indicates that your model is better, right? And most of the case, it doesn't matter which one you are going to select, right? So in this particular example, actually, it shows you regression problem. And then ideally in regression problem, what we are trying to do is we are looking for errors, right? So we need to have minimum as much as possible. So if that is the case, you can ask, okay, which algorithm you are going to select? This is error. Error should be minimal, right? So we are trying to identify which one is better. So then you can see, we can look for A, B, C, D. What I said was higher the better, right? Yes, error rates. So based on that, we can make a decision. So if you look at carefully, this is error rate. The minimum error rate you will see with the D. Then you have C, then we have A and B. So likewise, you can use it to identify, right, which measure. Right. Now, to end the model selection, right, remember, we need to have a balance between the complexity and the accuracy. So we need to focus on both the complexity of the model and also the accuracy. What do you mean by complexity? Now let's take a decision tree. If you have like one or two, nodes, it will be very, very simple. But let's say you have 30, 40, 50, then it will be really, really complex. So ideally what you observe is whenever the accuracy is, in this particular case, complexity is small, the accuracy is also small. The complexity high, the accuracy is also high. The second one is you can look for a prediction accuracy, right? So you have to find out the balance between these two. You have to look for complexity of the model as well as prediction accuracy. Okay, just to summarize this, a good model, when we say it's a good model, right? So what we mean by here is the use of simple model which achieves high accuracy. This is very, very important. Right. Okay, that's the theory part that I would like to discuss under this. So now let's focus on some of the implementation details. Right. Now you can see here that we have discussed, percentage split. Right. So the next one is you can use cross-validation. If you have enough data points, you better go here. But if you do not have enough of medium to small sizes, okay, you can go for cross-validation. So observe how we got for percentage split. Let's go for cross-validation. Let me click start. Okay, if you look at the outcome will be the same. Why it is same? Because you are using the same data. But you can observe, cross-validation accuracy. Previously, we got about 96.0784, whereas here you will get about 96%. And remember, in this particular case, this is actually repeated 10 times and you get an average accuracy. Right? So here are the details. Okay, I would like to go to the last part of this. In the confusion matrix, you will observe that. So diagonally, we will see the correct classifications. And the off-diagonal elements are the errors. So we have 4 to 6 misclassifications in the data set. Right. This part we have discussed, and then the measurements. Okay. Now for each class, now you can notice this will also calculate true positive rate. Remember what do you mean by true positive? Yes, the actual class is predicted correctly, right? So we got true positive. False positive. Then we have precision, recall, F measure, and so on, right? So you can actually observe these values when you're comparing. If you have a same data set and if you try multiple different algorithms, okay, you can look at this now. Right. So now I think you are comfortable with percentage split and the cross-validation. Next one. If you want to experimentally do this, I think we have discussed. So I'm going to select experimenter for the second part of this. So let me select, okay, experimenter. And I think we discussed last time how to use experimenter. We can click new experiment. And you can add the data first. So under the data, let me select iris. And here we can add some algorithms. So I'm going to select, let's say, tree structure. Okay, we have J40. I'm not going to change any parameters. I'm going to use as it is. And let me add one more. We have also select prism. So we'll say IP1, WebPrism IB1 may be naive base. Right, now we have 4 and we can try it out. So in this particular case, I have actually selected 10-fold cross validation and this will be repeated 10 times. So ideally, in this particular case, we are performing 10-fold cross validation 10 times. Okay, so we'll go to Run tab and click Start. Okay, so it says we cannot use Prism, so I'll be moving it. Sorry about this. So iris, we have numerical data, yes. So therefore we have to treat it separately. So we are using these three. We'll go back and click again. Right. So in my case now, when you go to run and when you click start, it started, finish without any errors. Once you finish this, go to Analyst tab and click on Experiment. What I do here is I'm getting the data from the experiment. So now you can, when you click experiment, you will see, okay, got 300 results. And then click on perform test. And ideally, you will get a comparison among the 3 classifiers like this. So in this particular case, what we are trying to see is whether there are any significant difference between the accuracies. So you can see that the first accuracy is based on the J48. Second one is nearest neighbor. Third one, naive base. So accuracies, if you look at very carefully, 3 accuracies about 94.73. Nearest neighbor about 95.4 and naive base is 95.53. And what this shows is it's in the middle, everything is 1, which means that there's no significant difference between any of these accuracies. They are slightly different, so you can use any of the algorithms to use in this case as the final model. Okay, so that's about it. Now I would like to give you a new data set and I want you to try building and find a best classifier, right? So that's what we are going to do. So I'm going to pause. So you can see that I have opened up the file using a notepad. So basically a text editor. So we need to slightly modify this file so that we can read it, right? We can read it from using WEKA. So it uses a special data format called ARFF, which is the default format using. So let me show you how to convert this. So this is, I'm going to do it manually so that you can understand each of these. Right. So let's start. So in this particular case, you can notice that the first column is animal name here, feathers, eggs, milk, and so on. So these are like other attributes. And finally, we have a type. So you have animal type like mammal, fish, invertebrate, bird, reptile, amphibian, and insect. So therefore, first, let's convert this, right? So here is what you need to do. I'm going to write down something. First of all, we need to provide a name for the data set. And as I told you in WEKA, we are using a special formatting instruction. So we use keyword relation, and then I will say this is data. So this indicates that I'm going to use the data set as data, right? Now for each and every column, I'm going to specifically provide. So these are called attributes. So I'm going to now introduce attributes. The keyword is attribute, right? And the first attribute is animal name. So I will use animal name space, and I'm going to say string because it's a name, right? So it's name of the animal. So therefore I'm going to use name string. Second attribute, I will specify the second attribute. So hair, basically whether animal has hair or not. And if you look at the column, you have true, false values. So that means you have specifically some Boolean values. So I will specify this attribute has two values. So true and false. So all the attributes, if you look at carefully, we have the same. So therefore, I will type. So third one, attribute feathers. Again, we have true and false. Attribute. Then we have eggs. Right. Actually, you don't have to, you can copy paste some. Right. The next one is milk. So I will put milk here. Next. They have air. Aquatic. So basically what I'm doing here is I'm specifying the attribute name and the possible values. So we have fins, here we have legs, right? So I will put legs. Then we have after legs, we have tail. Then we have after tail, we have domestic. Then we have cat size. Right. Final one is type. If you look at the type, you have various different types like mammal, fish, invertebrate, bird, reptile. So these are animal types. So I will give you the list. You don't have to, manually type it. So the last one, I'm going to say at attribute, and I will say type. And I have list all the different animal types, right? That part I will give it to you. So this is what I have. So the last line, right? I'll copy paste it to your chat, right? Okay, there is two. So what I have done, let me brief. First part, I gave a name for the dataset. Each attribute I have defined together with the values. The last one is the class. We call it type and list all the different attributes, different classes. Right. I can remove now this because this is the heading. So start of data, I'll use a special keyword data, which indicates that after that point, we'll have the data. Right. So first of all, let me know whether you have finished up to this point. We want to save this as a ARFF file format. So therefore, you have to be very careful when you're saving the text file. So let me save this. I'm going to click save as, and then inside this folder, I'm going to use double quotes. Remember, I will use the extension ARFF. So that way, I'm saving this as the format required for WEKA. Right. Let me save. So if I go back to the folder, so let me show you how it looks. So you should see something like this, right? So you should see it as a ARFF file. So this is text. Now this you can see it as a ARFF file. Right, now let me see whether I can open it. I'll go to WEKA, click Explorer. I'll click File Open. Okay, now I can open it up. Okay, there's a small error, I guess. Line 23, let me check. There's a one mistake I have made under the legs. It should be numeric because you have a number in this particular case. So let's try to open it again. I'm going to use Explorer. Okay, so it's a success now. So in this dataset is called zoo dataset. It's about different types of animal, and ideally it's a classification problem, and based on the different properties, we are supposed to classify animal type. So that's what we are trying to do. So when we open up, you can see the values. For example, if you take uh, so, first of all, class, Still there's issue. Okay, now I can see. So you can see here the number of classes. We have mammal 41, fish 13, invertebrate 10, bird 20, and so on. And the color is also the same. So the name, you don't see anything because it's just basically a number. We put it as a string. But if you take here, you can notice, yes, true, false, the counts, feathers, and so on. But if you take legs, it's a numerical data. So those are the things that you can observe. So if you select a particular attribute, and then it will show you how the distribution is looks, right? Based on the true false value, how the values are distributed. Now, if you want to see everything, you can go to visualize. Or you can click on here, sorry, visualize all. And you can see all the visualization for all the attributes, how the values are distributed. You can observe. If you click the visualize all here, now you can see based on the values, how they are separated. You can see very interesting observations. Some of the classes are purely separated. For example, the blue color is for mammals, right? If they have milk and if they lay eggs, so you can notice the mammals are the prominent. But then if you have feathers, the 20, I would say it's a bird. So you can visually see some of the information through this, right? There are a lot of information you can observe like this, particularly if you select an attribute. Let me close this. If you select something, then you can see whether there are any missing values. So observe here. So in this particular case, it will list out if there are any missing values, and it shows you that there are two distinct values, right? And then you can see the values are here. Of course, if you want to see the data, and if you want to see the open the file, you can go to Tools, ARFF Viewer. If you click on ARFF Viewer, and if you go to File, Open, and open your data set, you can see what is in the data. So now I'm going to go to the select the ARFF file. And when I choose the file to open, I can see the details. So you can see the data types as well, right? So it goes like this, and finally the type, right? Notice the different data types. So if you want to create a decision tree, so you can go to classify, choose trees. Okay. The problem with this one is I have to select the type. Okay, there are a few issues I think still we have. Let me see. So let's remove the animal name. So click on the animal name and click remove. It will be removed from the data set. So what has happened? We removed just one column from the data set. The reason for doing this is the data is not compatible. That was the issue because I have defined it as a string. So it expect me to type everything. So it's not practical. So therefore I have removed it. Now we have the remaining ones. Right. It was anyway one of the pre-processing techniques. If you remember, when you have unique attribute, it causes problem, especially when you are creating, if you're creating a decision trees, for example. So therefore, it's good that we have removed it. Right. Now we go to classify. Let's try it out. I'm going to select trees and let me select J40. Let me click on it. So you can see that I will get a tree structure. Let's visualize. Okay, so now it's looks like this. Let me put it to window. We can have a little bit higher font. Yes, fit to screen. Okay, now you can see how the classes are right defined. So if you look at very carefully, you can notice in my case, if you have feathers, feathers true means if you have feathers, yes, it is classified as a bird. If you do not have feathers, but milk is true, then it becomes mammal. No feathers, no milk, but then you check the backbone. If you have a backbone and then if you have fins, it classifies as fish. If you don't have fins, but you have a tail, then it's reptile. Don't have a tail, then it is amphibian. Similarly, no backbone, but if it is airborne, then it becomes insect. Not airborne, predator, true, invertebrate, false, whether you have legs. Okay, if you have less than or equal to 2 legs, it's invertebrate. Greater than 2, then it says insect. So similarly, you can observe the outcome from the zoo data. Right. That's the first part. So if you look at the accuracy, we have considered 10-4 cross validation accuracy. It is around like 92%. You can see true positive, false positive, precision, recall, F measure, all this information. But let me look at the confusion metric. This is very, very important. Right. So hope you remember the confusion matrix. So this side is actual labels and this is classified label. So what this means, 41 is what is available and what is classified. So actually we have 41 and classified as 41 as mammals. We have 13 fish, correctly classified as 13 fish. But if you take invertebrate, now you see a problem. Invertebrate, we have 10. Out of 10, 8 is classified as correctly as invertebrate. 2 is classified as insect. So you see a misclassification. Birds, correctly classified as birds. We have 4 reptiles, 3 plus 1. 3 is correctly classified, 1 is classified as insect. Amphibian, we have 4. 1 misclassification as a reptile. 8 insects. We have 8 insects. And 3 classified as invertebrate. 5 it is correctly classified. So you should learn how to read the confusion matrix. Right, I have a question for you. Can I apply ID3 here, ID3 algorithm for this data set? What do you think? Now the question was whether we can build the ID3 algorithm. So you can notice that it is grayed out. Gray out means you cannot apply. So if you carefully look at our data to apply, because ID3, if you have categorical data, right, nominal data. So these all are called nominal, but legs, if you look at it, it's numeric. Numerical data is not supported. So let's remove leg from the data set. Now, if you go to classify and click ID3, you will observe, right? You will observe ID3 is now, you can select. Actually, you can build the tree as well. You cannot visualize because it's ID3, but of course, but you can notice that the tree structure. Simply it says if you have milk, it's mammal. Otherwise, you can check whether you have feathers in bird. If the feathers bird, you can check whether black bone is true. And if you have fins, then fish and so on. Right. So what we can observe here is if you have integer attributes, then you cannot build a tree with ID3. ID3 is actually expect you have categorical data. Okay, so that's all what I have for today. So today's session, we talk about the very important part, which is I discuss all these numbers and what it means. And also we work with a simple data set, a text, and we discuss how to convert it to ARFF form. Right. So we'll continue the exercises next week as well. So for the time being, we'll stop for today and let's meet the same time next week. Thank you, guys. If you have questions, please let me know.